Hello. Welcome to Lecture 5 of my Mathematics of Lattice-Based Cryptography course. In this lecture, I'll explain why SIS and LWE, which are two fundamental problems in lattice-based cryptography, can be viewed as lattice problems. In the next lecture, I'll present the ring and module versions of these problems. Recall that the SIS problem is to find a small integer solution z to the linear system of equations az equals 0 modulo q. Here, small means that the coordinates of z are between minus b and b. And of course, z must be non-zero, otherwise SIS has a trivial solution. Let's define the SIS lattice to be the set of all integer solutions z to az equals 0 modulo q. It's not clear that this set is indeed a lattice, i.e., the set of all integer linear combinations of a set of linearly independent vectors in Rm. I'll next prove that the set is indeed a lattice, and then I'll proceed to determine its rank, volume, and a basis. To prove that the set is a lattice, I'll use the following equivalent definition of a lattice. The equivalence of this definition to the definition of a lattice given in the previous lecture requires proof. However, that proof is relatively complicated, so I won't do it here. Okay, so the alternate definition of a lattice is the following. A lattice L is a discrete additive subgroup of Rm. L is an additive subgroup of Rm means that L is non-empty and closed under addition and negation. L is discrete means that for each lattice element x, there exists a small ball of radius epsilon centered at x that contains only one lattice element, namely x. It's now easy to check that the SIS lattice satisfies this definition of a lattice. Establishing the discreteness of the set is straightforward, since the lattice is a subset of Zm, i.e., all coordinates of lattice elements are integer valued. I'll next show that the SIS lattice has rank m, so it's a full rank lattice. Now, the set QZM is a set of all vectors, all of whose coordinates are integer multiples of q. You can check using the second definition of a lattice, that QZM is a lattice. And indeed, it's a sublattice of the SIS lattice, since every vector in QZM is congruent to 0 modulo q, and thus satisfies the system of equations az equals 0 modulo q. Now, the q multiples of the unit vectors are in the sublattice QZM, and are linearly independent over the real numbers. Thus, QZM must have rank m. Of the SIS lattice must also have rank m. That completes the proof. The SIS lattice is an example of a Q-ary lattice. In other words, an integer vector z is in the lattice if and only if z modulo q is in the lattice. Here, z modulo q is the vector obtained by reducing all the coordinates of z modulo q. So basis matrix for QZM is q times the m by m identity matrix. Hence, the volume of QZM is q to the m. And since QZM is a sublattice of the SIS lattice, it follows that the SIS lattice has volume at most q to the m. In fact, the SIS lattice has volume q to the n, where n is the number of rows of the matrix A. The proof uses some standard results from group theory, in particular, the theory of free abelian groups. A good reference for these results is section 1.6 of the Algebraic Number Theory book by Stewart and Toll. If you don't have a background in group theory, feel free to skip this proof and proceed to the next slide. Okay, now the integer lattice Zm and the SIS lattice are free abelian groups of rank M. This means that Zm and the SIS lattice are both isomorphic as groups to a direct product of M copies of the integers. Theorem 1.17 of Stewart and Toll's book implies the following. Since the SIS lattice is a subgroup of Z to the M, and they both have rank M, the quotient group Zm modulo the SIS lattice is finite. Moreover, the size of this quotient group is equal to the volume of the SIS lattice. So, to determine the volume of the SIS lattice, we need to compute the size of the quotient group. In other words, the number of distinct cosets of the SIS lattice in the integer lattice. Now, by definition of cosets, two integer vectors x and y determine the same coset if and only if x minus y is in the SIS lattice. In other words, ax equals ay modulo q. So, to determine the number of cosets, we need to determine the dimension of the column space of the matrix A modulo Q. Since A was randomly selected, we can assume that A modulo Q has full rank n. Thus, the column space of A modulo Q has dimension n, and so the column space has size q to the n. Thus, the SIS lattice has volume q to the n. I'll next describe a basis for the SIS lattice. Since the SIS lattice has rank m, we need to find m linearly independent lattice vectors that span the SIS lattice. We're assuming that the n by m matrix A has rank n over ZQ. Suppose, without loss of generality, that the first n columns of A are linearly independent over ZQ. Thus, A can be row-reduced to a matrix A tilde in canonical form, with the identity matrix in the left, and an n by m minus n matrix A bar on the right. Now, let C be this m by m integer matrix. Then C is a basis matrix for the SIS lattice. So the columns of C are a basis for the SIS lattice. To prove this, first note that since A and A tilde are row equivalent, they have the same null space modulo Q. Hence, A and A tilde have the same SIS lattice. We'll find a basis for the SIS lattice of A tilde. Now, you can check that each column of C is in the null space of the matrix A tilde. Hence, each column of C is in the SIS lattice of A tilde. Moreover, the columns of C are linearly independent over the real numbers, since the determinant of C is q to the n, which is non-zero. Thus, we can conclude that C is a basis matrix for a full-rank sublattice L of the SIS lattice of A tilde. Now, L has volume q to the n, since C has determinant q to the n. But we showed that the SIS lattice of A also has volume q to the n, and thus the SIS lattice of A tilde also has volume q to the n. So, since L is a sublattice of the SIS lattice of A tilde, and they have the same volume, it must be the case that L equals the SIS lattice of A tilde. So we have proven that C is a basis matrix for the SIS lattice of A. SIS is equivalent to the following lattice problem. Find a non-zero vector Z in the SIS lattice with basis matrix C. Here, short means that the coordinates of Z are between minus b and b. Equivalently, the infinity norm of Z should be at most b, where the infinity norm of a vector is the maximum of the absolute value of its components. In the literature, SIS hardness is usually studied using the Euclidean norm instead of the infinity norm. The Euclidean norm and infinity norm are closely related. For all vectors z, the Euclidean norm of z is at least equal to its infinity norm, and at most equal to square root of m times its infinity norm. It follows that SIS and the Euclidean norm formulation of SIS, which I'll present next, are also closely related. The Euclidean norm formulation of SIS, which I'm calling SIS2, is the following. Given a randomly selected n by m matrix A over the integers modulo q, where m is greater than n, and the bound beta, which is much smaller than q, find a non-zero solution z to az equals 0 modulo q, where z has Euclidean norm at most beta. Note that the SIS parameter b has been replaced with the parameter beta. An equivalent lattice formulation of SIS2 is the following. Given a randomly selected n by m matrix A over the integers modulo q, find a non-zero vector of norm at most beta in the SIS lattice. Now, by Minkowski's theorem, the length lambda1 of the shortest non-zero vector in the SIS lattice is at most the square root of the dimension m times the mth root of the volume, which is q to the n. We'll assume that beta is at least the square root of m times q to the n over m, whereby an SIS2 solution is guaranteed to exist. Now, by the Gaussian heuristic, the length of the shortest non-zero vector in the SIS lattice is expected to be this quantity. Thus, SIS2 is an instance of a prox SVP in the SIS lattice, with the approximation factor gamma equals beta divided by the expected length of the shortest non-zero vector in the lattice. This shows that hardness of a prox SVP is a fundamental requirement for the hardness of SIS. It's perhaps reasonable to conjecture that SIS is hard in the worst case. However, an SIS instance is generated by selecting a matrix A uniformly at random. So, in cryptographic applications that rely on SIS hardness, we need the assurance that SIS is always hard, except perhaps with negligible probability. In other words, we need the assurance that SIS is hard on average. Another concern with SIS is that the corresponding approx SVP instance is a rather special instance of approx SVP. Namely, the SIS lattice has a basis matrix of a special form, which is almost upper triangular except for the Q's along the top left diagonal. So one might be concerned that even though approx SVP might be hard, it might be easy for the special lattices that arise from SIS instances. In his landmark 96 paper, Aitai proved that SIS is hard on average under reasonable assumptions. Namely, he proved that if approx SIVP is hard in the worst case, then SIS is hard on average. Such a reduction is called a worst case to average case reduction. Aitai's reduction is much too complicated for me to cover in these lectures. A high-level outline of the reduction is the following. Beginning with any n-dimensional lattice basis D, Aitai showed how to generate a random instance of SIS, with the property that an SIS solution Z can be used to find a solution to approx SIVP in the lattice generated by D. This shows that if SIS can be solved on average, then SIVP gamma can be solved in the worst case. Since the assumption that approx SIVP is hard in the worst case is a reasonable assumption, we have a provable guarantee that SIS is hard on average. Aitai's worst case to average case reduction for SIS is a remarkable result. However, it must be emphasized that the guarantee is an asymptotic one. Also, the reduction is highly non-tight. Here, non-tight means that the reduction algorithm that solves a prox SIVP using an SIS solver is very inefficient. Here is the statement of a refinement of ITI's result that was proven in 2004 by Michiancho and Regev. For any m that is on the order of n log n, there exists a q that is at most n squared times log n, such that for any gamma that is at least n log n, solving the Euclidean norm version of SIS on average is at least as hard as solving a prox SIVP in the worst case. The asymptotic nature and non-tightness of the theorem means that the theorem cannot be used to select SIS parameters with a useful security guarantee for practical applications. To summarize, we have seen that SIS can be considered to be a lattice problem for two reasons. First, SIS is equivalent to solving a prox SVP in SIS lattices. Although SIS lattices are special kinds of lattices, no algorithm is known for solving a prox SVP in SIS lattices that is any faster than the best algorithm known for solving a prox SVP in general lattices. The fastest algorithm known for solving a prox SVP in general lattices is the BKZ algorithm, which is a refinement of the LLL algorithm. Running time estimates of BKZ are used to select concrete parameters for SIS to achieve a desired security level. Second, average case SIS has been proven to be at least as hard as worst case of prox SIVP. Although this result is remarkable, the hardness guarantee is an asymptotic one, so its relevance to the hardness of SIS in practice is not clear. I'll next explain why the learning with errors problem is considered a lattice problem. Recall that the LWE problem is to find a solution S to AS plus E equals B modulo Q, which is a system of noisy linear equations modulo Q. The error vector E has small components, namely integers between minus b and b. Let's define the LWE lattice LA to be the set of all integer vectors y for which A times Z equals y modulo Q for some integer vector Z. The set LA is a full-rank integer Q-ary lattice in Rm. To prove that LA is a lattice, you can verify that LA is a discrete additive subgroup of Rm. Next, show that QZM is a sublattice of LA, which confirms that LA is Q-ary and has rank M. I'll next proceed to describe a basis for the LWE lattice. Let A1 be the matrix consisting of the first n rows of A, and let A2 be the matrix consisting of the last m-n rows. I'll suppose that A1 is non-singular modulo Q. This will be the case with high probability. Define D2 to be the matrix A2 times A1 inverse modulo Q, and note that D2 has m-n rows and n columns. Next, define D to be this m by m matrix. Then I claim that D is a basis matrix for the LWE lattice and has volume q to the m minus n. First note that D has determinant q to the power m minus n, which means that the columns of D are linearly independent over the reals. Now, let y be a length m integer vector comprised of y1 and y2. By definition of the LWE lattice, y is a lattice vector if and only if y equals az modulo q for some integer vector z. Now, y equals az modulo q if and only if y1 equals a1z and y2 equals a2z mod q for some integer vector z. Since a1 is invertible, we have z equals a1 inverse times y1 modulo q. And after a substitution, we get the equivalent condition y2 equals a2 times a1 inverse times y1 modulo q. This in turn is equivalent to y2 equals d2 times y1 plus q times c for some integer vector c. So we have y equals d times y1c. So y is an integer linear combination of the columns of D. Since the columns of D are linearly independent, it follows that the columns of D are a basis for the LWE lattice. For an LWE instance ABSE, the vector y defined as y equals as modulo q is in the LWE lattice. Moreover, the vector b minus y equals e modulo q. Since the components of E are between minus b and b, the length of E is at most square root of m times b. Hence, the distance between b and y is at most the square root of m times b. So b is quite close to the lattice point y. Thus, LWE is a special instance of the following lattice problem called the bounded distance decoding problem. Given an m-dimensional lattice and a vector b, with the guarantee that there is a unique lattice point y within distance alpha of b, find the lattice point y. I said that LWE is a special instance of BDD, since the LWE lattice is not a random lattice. Indeed, the LWE lattice is a Q-ary lattice, which is quite special. I'll next show how BDD can be reduced to solving the shortest vector problem. I'll suppose that the BDD instance has distance guarantee alpha, which is less than lambda 1 of L divided by the square root of 2. Recall that lambda 1 is the length of a shortest non-zero vector in lattice L. Now define d' to be this matrix. Notice that d' has non-zero determinant, since D has non-zero determinant and alpha is non-zero. Thus, D' is the basis matrix for a lattice L'. The vectors in L' are of this form, where V is in the original lattice L and C is an integer. Let's first notice that for V equals Y and C equals 1, the vector tilde V is an L'. Since the length of tilde V is at most the square root of 2 times alpha, it follows that lambda 1 of L' is at most the square root of 2 times alpha, which by assumption is less than lambda 1 of L. I'll next characterize the non-zero vectors of shortest length in L'. Suppose that V' is a vector in the lattice L' of minimum length lambda 1 of L'. Now, if C equals 0, then V' has the same length as V, which has length at least lambda 1 of L, since V is an L, which we saw is greater than lambda 1 of L'. So the length of V' is greater than lambda 1 of L', a contradiction. Next, suppose that the absolute value of C is at least 2. Then, looking at the last component of V', we see that the length of V' is at least 2 times alpha, which is greater than the square root of 2 times alpha, which is at least lambda 1 of L'. So the length of V' is greater than lambda 1 of L', a contradiction. Hence, C must be plus or minus 1. Now, suppose that C equals 1. Then V' is of this form, where V is in L. If V is not equal to Y, then the length of V minus B is greater than the length of Y minus B, since Y is the unique lattice vector closest to B. Hence, V' is longer than tilde V. This contradicts the assumption that V' is a non-zero vector of smallest length in L'. Hence, it must be the case that V equals Y. the case c equals -1 is similar to the case c equals 1 except for sign. So we conclude that tilde v and its negative are the only vectors of shortest length λ1 in the lattice L primed. To summarize, one can solve a BDD instance with distance guarantee alpha in a lattice with basis matrix D by solving SVP for the lattice with basis matrix D primed. In the literature, this method of solving LWE is called a primal attack using a Canaan embedding. As with the SIS problem, it's perhaps reasonable to conjecture that LWE is hard in the worst case. However, an LWE instance is generated by selecting A, S, and E uniformly at random. So in cryptographic applications that rely on LWE hardness, we need the assurance that LWE is always hard, except perhaps with negligible probability. In other words, just like with SIS, we need the assurance that LWE is hard on average. A second concern with LWE is that the corresponding SVP instance is rather special. So one might be concerned that even though SVP might be hard, it might be easy for the special lattices that arise from the LWE instances. In his seminal 2005 paper, Regev proved that LWE is hard on average under reasonable assumptions. Namely, he proved that if a prox SIVP is hard in the worst case against quantum attacks as well as classical attacks, then LWE is hard on average. This shows that if LWE can be solved on average, then a prox SIVP in the worst case can be solved on a quantum computer. Since the assumption that a prox SIVP is quantumly hard in the worst case is a reasonable assumption, we have a provable guarantee that LWE is hard on average. However, as with ITI's worst case to average case reduction for SIS, Regev's reduction for LWE is asymptotic and is highly non-tight. For a concrete analysis of Regev's reduction, see section 5 of my paper, Another Look at Tightness 2 with Chatterjee, Koblitz, and Sarkar. I should note that in Regev's worst case to average case reduction, and also in much of the cryptographic literature on LWE-based protocols, the components of the LWE error vector E are generally drawn from certain Gaussian distributions, and not from uniform distributions. However, for the sake of simplicity, I didn't use Gaussians in my lectures. Also, Kyber and Dilithium don't use Gaussian distributions, but instead use uniform distributions and so-called central binomial distributions. In summary, we have seen that LWE can be considered to be a lattice problem for two reasons. First, LWE can be reduced to solving an instance of SVP in a special lattice derived from the LWE lattice. Although LWE lattices are special kinds of lattices, no algorithm is known for solving SVP in these lattices that is any faster than the best algorithm known for solving SVP in general lattices. The fastest algorithm known for solving SVP in general lattices is the BKZ algorithm. Running time estimates of BKZ are used to select concrete parameters for LWE to achieve a desired security level. Second, average case LWE has been proven to be at least as hard as quantumly solving a prox SIVP in the worst case. Although this result is remarkable, the hardness guarantee is an asymptotic one, so its relevance to the hardness of LWE in practice is not clear.